have actually mentioned this one already, but just to formalise the idea, when we've got that square root of two squares, so a squared plus x squared, then I can use a tan theta, turn it into a trig identity, which allows me to get the two terms, make it one. If it was a squared minus x squared, I'd go with a sine or a cos, doesn't really matter which one. And if it was the other way around, then I'd go with a sec. But again, that allows me to turn the two terms into one squared term, and then the square root of the square cancels and away we go. So here's the actual standard integral, so we'll see where it actually comes from. So 1 on the square root of a squared plus x squared. So it's in the form a squared plus x squared. I'm going to go x equals a tan theta, which means dx would be a sec squared theta to theta. So subbing in for the dx, we get a sec squared. Then on the bottom I've got a squared plus a squared tan squared. But that'll become a squared sec squared. We've got the square root of a squared sec squared. So that would be a sec, but the a sec will cancel with the a sec squared on top, leaving me with just sec theta. Integral of sec, log of sec plus tan. So log of sec plus tan. Now how do I substitute back in? Well, I'll draw myself up a triangle. We know x over a is tan theta. The hypotenuse, no coincidence, turns out to be the surd. And now I can just substitute in. So sec is the square root of a squared plus x squared over a. Tan is x over a. The standard integral, you will notice when you see it, doesn't have the over a. And that's because they've used their log laws. Because they're basically saying, oh, well, that'll be minus log a. Log a is just a constant. So we could just write it as x plus the square root of a squared plus x squared plus a constant. So that's where that one comes from. What was the other one we had? We had the square root of a squared minus x squared. No, that was inverse sine. So it must have been x squared minus a squared. Similar sort of idea we'd do. Okay, so let's do this one. X on the square root of 1 minus x squared. So 1 minus x squared, in this case I'll make x equal to either sine or cos. It doesn't matter, I went for sine. So cos theta to theta will be the x. So I get sine theta cos theta to theta on the top. Square root of 1 minus sine squared. 1 minus sine squared is cos squared. Square root of cos squared would be cos, which will cancel with the cos, leaving me with just sine theta. Integral of sine is minus cos. Now we need to substitute back in, so I'll just draw myself a little triangle. X over 1 is sine, so the adjacent is the square root of 1 minus x squared. Cosine is adjacent over hypotenuse. You get minus the square root of 1 minus x squared, and that's when you then kick yourself if you went and used this method and you go, oh yeah, x is just the derivative of minus 2. I could have just gone derivative times, oh damn, why didn't I spot that instead of wasting all this time? But anyway, another way we could do that particular integral. The square root of x squared plus 3. Okay, so a squared plus x squared, I'm going to make it root 3 tan theta. So dx is root 3 sec squared theta. So subbing in, the first one becomes, the surd is now 3 tan squared plus 3, which is 3 sec squared, but the square root of 3 sec squared is root 3 sec. So I've gone straight to root 3 sec there. Dx, root 3 sec squared. I now go 3 times the integral of sec cubed. That's the one we did by parts. So okay, I'm going to split it up. Sec with sec squared. My u will be sec, so du is sec tan. dv is sec squared, so v is tan. I've got 3 lots of uv, sec theta tan theta, minus 3 times the integral of v to u, so 3 times the integral of sec theta tan squared theta. Sec theta tan squared theta. Well, I'll change the tan squared theta into sec squared theta minus 1. I've also broken it up into 2 integrals at the same time. And the integral of sec is sec tan. But hang on. If you look at my third line says 3 times the integral of sec cubed. So 3 times the integral of sec cubed is equal to this one. So it's another one of these situations where I can treat it like an equation. I might just substitute in first of all. So rearranging all that. 3 sec theta, square root of x squared plus 3 on root 3 times tan theta, x on root 3. Sec cubed becomes, look, 3 lots of sec cubed is equal to, go to the first line, square root of x squared plus 3. So I've just changed my 3 lots of sec cubed to be the square root of x squared plus 3. Plus 3 log sec plus tan. Move the square root of x squared plus 3 over. I now have 2 lots of the square root of x squared plus 3. So divide everything by 2. And I think we've got our answer. I notice I haven't underlined it because I probably said, oh look, it's over the square root of 3. Did I get rid of it? Yeah, I did. Because I absorbed the log of the square root of 3 into the constant. I mean, it doesn't really matter whether you do that or not. I mean, they're both correct answers. There are no questions in the Cambridge on this particular idea, but Patel's got an exercise with some of these to have a go at. So we'll just add those ones to our list.